Hello dear students, today we are going to discuss about fluorescence spectroscopy. Fluorescence spectroscopy is a method in which we are going to check for the fluorescence. Fluorescence is a phenomenon in which whenever a molecule or whenever an electron is going to get excited, it goes to the excited state by undergoing electronic transition. After few minutes, after few little time being at that particular higher electronic transition state, so the electron is going to come back to the ground state. While coming back to the ground state, it's going to emit the light or they emit the electromagnetic radiation, so which is equal to the amount of energy which is going to get means which is need to be get released in order to form a in order to get into the lower energy state or into the ground state. So this energy which is released in the form of electromagnetic radiation is called as the fluorescence. This phenomenon is called as the fluorescence, and this fluorescence phenomenon is going to be used in order to understand that particular molecule. You can see here, so when the energy is input is going to be there, electron gets into the excited state and that is absorption, whereas from the excited state, when it is coming back to the ground state, it is going to give out the electromagnetic radiation, that is the fluorescence. So there will be excitation, so which is going to happen by the absorption of energy, and this energy absorption can happen at different range of electromagnetic radiation depending upon the molecule. From ground state it gets into excited state and it can come back to the ground state. See, while coming back to the ground state, it can also get means it can find means when the electron is going to be there at the excited state, it will spend a small amount of time, so it's going to spend a very small amount of time, and then from the excited state it's going to come back to the ground state. While coming back to the ground state, one second, so it is going to come back to the ground state, it's going to emit the energy. And here sometimes this energy which is going to get emitted can also be in the form of non-radiating transitions can also happen. That is, it can go from one high energy level to the next sub level, okay, and very small amount of energy is going to get released, and the electron is going to get excited. So like this it can go on coming to the ground state and give rise to the radiation. So fluorescence emission, finally when the electron is going to probability and the photon energy is going to be the h nu is emitted, so returning to the of the fluorophore, so it's the ground state, and due to energy dissipation during the excited state lifetime in the form of non-radioactive relaxation, the energy of this particular photon is going to be lower, and therefore the energy is going to be of longer wavelength. Generally the fluorescent energy or fluorescent radiation is going to be in the longer wavelength than that of whatever the radiation it is going to get absorbed. So lambda Stokes is equal to maximum emission minus maximum absorption. So you can see here there will be some amount of energy which is going to get released as non-radiating energy. So that happens when the electron is going to get relaxed itself at the vibrational energy levels, and it can just go by step and can release the energy into the without undergoing any means without emitting the radiations. So it can happen by non-radiating emission as well as by quenching. So whereas on the other hand, the radiation can get emitted in the form of fluorescence. So therefore we can come across with a change in the lambda emitted and lambda absorbed. So the difference is going to give you the Stokes shift. So you can see energy given, electron excited, it's going to undergo relaxation by undergoing small vibrational changes, and then it suddenly drops into the ground state and releases the fluorescence. So the relaxation time is called as fluorescence lifetime. It is going to be approximately 1 to 25 nanoseconds. And the wavelength which is going to get released when the fluorescence get emitted, it will be of longer wavelength. So we come across with here like something called quantum yield of efficiency of fluorescence. So quantum yield or efficiency of fluorescence is nothing but it is the ratio of the energy absorbed and energy emitted to energy absorbed. So we also call the radiation which is being emitted, so it's which we consider as a fluorescence decay. So all of the decay pathways that contribute to the efficiency of fluorescence or quantum yield are sensitive to the environment in which the fluorophore is present. Fluorophore means that is the part of that particular molecule which is going to involve in the absorption of radiation. So the environment which can affect is the solvent, temperature, and nearby resonating electrons. If there is any other electron which is going to be present nearby other than the one which is excited, so that can also, the resonating one electrons can also have a profound effect on the fluorescence which is going to be coming out and the quantum yield. And this quantum yield is going to be a very important factor. It can also be expressed as a function of rate of competing decay process, and you can see this is the formula which we can use to determine the quantum yield. Ke is the rate of radiative decay, not radioactive, sorry, radiative decay, and Ki is the rate associated with the radiative process, means without giving fluorescence. So non-radiative processes are going to be either through collisional quenching, it depends upon temperature. With more temperature, collision becomes more, and energy is going to get released not by radiation, but instead it's going to get lost in the form of collision transfer. And there is near dipole, that is solvent or a quencher, can also affect the electron, interact with the nearby ground state dipole electron, and loses its energy. And internal conversion within the fluorophore also, electron can lose the energy internally through direct interactions with the other electrons, which are, and thereby it can lose energy. There is a fluorescence type lifetime, so that means the period for which an electron stays in the excited state before emitting the fluorescence or the photon of energy. So this fluorescence lifetime is equal to, so population of electrons which get excited and initial population of electron of excited, so that gives you the fluorescence lifetime, and lifetime is an inverse of rate constant. So fluorescence lifetime is commonly used as an imaging technique because it minimizes the effect of photon scattering and used for the study of different biomolecules. So lifetime typically of 1 to 30 nanoseconds. Another important factor which we are going to come across is the fluorescence anisotropy. Fluorescence anisotropy, it results from the preferential absorption of light that is polarized in the same plane as the excited. So you can see here, this is how the fluorescence anisotropy is going to be seen, and during the relaxation phase, the analyte will tumble in solution, and the plane polarization of photons emitted will be reflect the new random orientation. So it means the plane in which the light is going to get absorbed and the plane in which the light is being emitted, they can be of different one, and anisotropy talks about it, and the amount of anisotropy we can measure, and a real fluorophore we must deal with the fluorescence relaxation or limiting anisotropy. Then we come across with intrinsic fluorescence in case of protein. Protein have a lot of fluorophore part within it. The most biological molecules, they essentially non-fluorescent, whereas DNA and RNA are very weakly fluorescent at 330 nanometer. But whereas The amino acids like phenylalanine, tyrosine, tryptophan having more number of delocalized electrons or pi electrons shows good amount of fluorescence. You can see absorption at 257 and emission at 282 for the phenylalanine with the efficiency of 0.04. Like that, others are also having different fluorescence capacity. Tryptophan fluorescence, again, absolute fluorescence intensity doesn't tell anything about the specific about the environment in which the fluorophore is there. So but in case of tryptophan, the fluorescence at 345 nanometer, it means even it is in water, but at 330 if it is going to be a polar solvent. So most of circumstances tryptophan fluorescence is going to be reduced upon exposure to water, but not always. So this particular aspect people are using to understand the environment of that particular protein of the tryptophan which is present. So the factors which can commonly quenched by the two factors, the tryptophan fluorescence get quenched. So that is one by proximity of to the protonated acids like aspartic or glutamic, and proximity to the resonating ligand like heme. So there are a number of artificial fluorophores people are going to be using. So whenever we want to study something which is not having intrinsic fluorescence by itself, people are going to add the fluorescent molecule by forming a covalent linkage to the other molecule under study, and for that people uses fluorescent probes, and there are few of artificial fluorescent probes people are using. These are the few of the probes which are being used covalently and as well as non-covalently. Another important factor which you are going to be using in the study, or means in the fluorescence studies, are fluorescent resonance energy transfer, FRET. FRET is a very important technique. It is being used very widely in the study of biomolecules, and particularly in the study of that is the interaction studies and all. So in FRET what we see is there will be transfer of energy occurs when one fluorophore donates its excitation energy to the second fluorophore, and the efficiency of FRET pair depends upon the overlapping integral between the emission spectrum and of the donor and the absorption spectrum of the acceptor. So FRET probes, like people are using GFP family proteins as FRET probes, and a number of proteins which are being used, and this is how the FRET studies are being done. So I'll stop here. I'll get into the instrumentation and the applications in the next video. Thank you.